Hi friends, welcome back on our YouTube channel. Today in Statistical Mechanics we are going to discuss about ideal gases in microcanonical ensemble. We already know about canonical ensemble, microcanonical ensemble and also about grand canonical ensemble. The link of all these lectures are given in description box. Now ideal gases in microcanonical ensemble. So let's start ideal gases in microcanonical ensemble. So here we will discuss about ideal gases in microcanonical ensemble. Let a system be made up of n identical non-interacting particles. Let Hamiltonian of the system be H equal to sigma I equal to 1 to n pi square upon 2m. Here m is mass of the particle and pi is the linear momentum of ith particle, and also pi square equal to pi dot pi, because vector a dot vector a equal to a square, so pi dot pi equal to pi square. Here a vector pi is the momentum operator of ith particle. In nature, a system of n identical particles form either a Bose system or a Fermi system. Bose system means a system which has bosons or Bose particle, whereas Fermi system is a system which contains fermions or Fermi particles. Now, what is Bose system? In this system, a complete set of eigenfunction is the collection of those eigenfunctions of H that are symmetric under an interchange of any pair of particle coordinate, and the particles forming this system are known as bosons or Bose particle. Now, what is Fermi system? In this system, a complete set of eigenfunctions is the collection of those eigenfunctions of H that are antisymmetric under an interchange of particle coordinate, and the particles forming this system are called fermions or Fermi particle. At high temperature, the thermodynamic behavior of Bose system and Fermi system approaches to a third system, and this system is known as Boltzmann system. So, at low temperature, there are two systems, Bose system and Fermi system, but at high temperature, the behavior of both these systems approaches to a third system, and this system is actually Boltzmann system. For study of ideal gases in microcanonical ensemble, we should find the number of states gamma E of the system having an energy eigenvalues that lies in the range of E and E plus delta E. Any energy eigenvalues or a level of an ideal system is a sum of single particle energies given by EP equal to P square by 2m. So, any energy eigenvalues or a level of an ideal system is actually sum of single particle energies, and these energies are given by EP equal to P square by twice m. Now, EP equal to P square by twice m and P equal to magnitude of vector P. And what is vector p? Vector p is actually momentum eigenvalue of the single particle. So this is actually magnitude of vector p, and vector p is actually momentum eigenvalue of a single particle. Also, vector p equal to 2 pi h cross upon L vector n. And what is h cross? H cross is actually reduced Planck's constant, and it is given by h upon 2 pi. Here h is Planck's constant and its value is 6.62 into 10 to the power minus 34 joule second. So if we divide h by 2 pi, that is 2 into 3.14, then this will be 1.05 into 10 to the power minus 34 joule second. This vector n is actually a vector whose components are 0 or plus minus integers, and L is actually cube root of V. So L equals to V raised to 1 by 3. And what is V? V is volume of this system. So L is actually the side of a box whose volume is V. If V tends to infinitive or volume is very large, then the possible values of P form a continuum. And in this case, sigma P will be replaced by P upon H cube integration d3P, or V upon H cube integration d3P is actually sigma P. So if V tends to infinitive, the possible values of P form a continuum, and in this case sigma P will be replaced by this one. Let there be Np particles having momentum P in the state under consideration. Therefore, total energy of the state will be E equal to sigma P Ep Np, and the total number of particles of the state will be N equal to sigma P Np. So in this case, total energy of the state will be E, and E equal to this one, and the total number of particles of the state will be N, and N is given by this equation. Here, for convenience, we use spin-less particles. For spin-less particles, the allowed values of Np for a state of the system is given by 0, 1, 2 and so on for bosons, whereas for fermions its value will be 0 and 1. So for spinless particles, the allowed values of Np for a state of the system will be 0, 1, 2 and so on for bosons, whereas its value for fermions will be either 0 or 1. Since Boltzmann system have both the cases, so for a Boltzmann's gas, Np equal to 0, 1, 2, 3 and so on. So for Boltzmann's gas, we combine these two values, and therefore for a Boltzmann gas, Np will be 0, 1, 2, 3 and so on. Since Np in curly bracket is actually set of occupation number specifying a state of an ideal system, so set of occupation number will be factorial n divided by pi p factorial np, state of n particle system. Since an interchange of the momenta of two particles in the system lead to a new state, but it leaves set of occupation number unchanged, and since Ep equal to p square by twice m, so as V tends to infinitive, the energy levels given by this equation form a continuum. Which equation? This equation. So we divide the spectrum of EP into group of levels containing G1, G2, G3 levels in E1, E2, E3 and so on respectively. So as V tends to infinitive, the energy levels given by this equation form a continuum. So we divide the spectrum of EP into group of levels containing these levels, and the energies corresponding to these levels are this one. Here we are showing continuum. So this is actually division of the single particle energy spectrum into cells. So this is G1, this is G2, G3 and here GS, and this whole thing is actually a continuum. Each group is known as cell. The average energy of each cell is EI. Let Ni is the occupation number of ith cell. It is actually sum of Np over all the levels in the ith cell. Now let W is the number of states of the system corresponding to the set of occupation number Ni. So this is actually number of states of the system corresponding to the set of occupation number given by this Ni. Therefore, gamma E is equal to sigma Ni Wi. Since gamma E is this one and total energy of the system equal to sigma I EINI and the total number of particles n equal to sigma INI. In Bose gas and Fermi gas, the interchanging of particles in different cells does not lead to a new state of this system. So W equal to pi I omega I, because in Bose gas and Fermi gas, on interchanging the particle in different cells, we does not have any new state of the system. So W is given by this equation. But in Boltzmann gas, if we interchange the particle in different cells, then we have a new state of the system and we consider all n particles together. So in this case, W will be pi I Gi raised to Ni divided by factorial Ni. Now, first of all, Bose gas. In this system, each level can be occupied by any number of particles. So these are our subcells. So this is subcell 1, 2, 3. This is subcell Gi minus 1 and this is subcell Gi. And these subcells are divided by partitions. So these are partitions, and we know that in Bose system each level can be occupied by any number of particles. So here the number of particles 2, here 1, here 2, and any cell can have any number of particles. Now it is clear from this diagram that ith cell have Gi subcells with Gi minus 1 partitions. So first partition, second partition, third partition, and this is our Gi minus 1 partitions. So ith cell have gi subcell. First subcell, second, third. This is gith subcell. So ith cell have gi subcell with gi minus 1 partitions. A box divided into gi section and the particles are distributed among these sections. Therefore, omega I is number of permutations of the Ni particle plus gi minus 1 partitions that give rise to distant arrangement. So, number of permutations of the Ni particle plus gi minus 1 partitions that give rise to distant arrangement provide us omega I. So omega I equal to factorial Ni plus gi minus 1 divided by factorial Ni factorial gi minus 1. And since W equal to pi I omega I, so Wi will be pi I factorial Ni plus gi minus 1 divided by factorial Ni factorial gi minus 1. So we take pi I of this omega I, so W will be this one. Now Fermi gas. So if we have Fermi gas, then what will be the value of W? In this system, the distribution of Ni particles among the Gi states can be done in the following way. The first particle can be put in any one of the ith level by Gi waves. Since Fermi system or Fermi gas obey Pauli's exclusion principle, and according to this principle, no more particles can be assigned to that filled state. Thus, the second particle can be put in rest of the Gi minus 1 levels by Gi minus 1 waves. So first particle can be put in any one of the ith level by Gi waves. Now, one level is filled, so the second particle can be put in rest of the Gi minus 1 level by Gi minus 1 waves. Therefore, the number of waves in Ni particles can be assigned to Gi states will be equal to Gi into Gi minus 1, Gi minus 2 up to Gi minus Ni plus 1. Now, if we multiply it by factorial Gi minus Ni and again divided by factorial Gi minus Ni, then this will be factorial Gi. So, the total number of waves in Ni particles can be assigned to Gi states will be factorial Gi divided by factorial Gi minus Ni. Since the identical particle do not give distinct distribution, therefore the required waves are omega I equal to factorial Gi upon factorial Gi minus Ni and W equal to pi I omega I, and omega I is this one. So W equal to pi I factorial Gi upon factorial Gi minus Ni. Now, if the gas is actually Boltzmann's gas, then what will happen? In Boltzmann distribution, the particles are distinguishable and distinguishable elements are divided into groups such that N1 plus N2 plus N3 plus Ni equal to N. So the total number of particles will be N, and N equal to N1 plus N2 plus N3 up to Ni. Suppose first of all we choose N1 particles out of capital N, and this can be done by NCN1 waves, or this will be equal to factorial N divided by factorial N1 factorial N minus N1. Now, N1 particles are already arranged. So, remaining N minus N1, and we want to choose N2 particles in second state. So, this can be done by N minus N1 C N2 ways. And this will be equal to factorial N minus N1 divided by factorial N2 factorial N minus N1 minus N2. Therefore, the number of ways in which particles in different states may be exchanged, leaving the total number in each state fixed, is given by factorial n divided by factorial n1 factorial n minus n1 into factorial n minus n1 divided by factorial n2 factorial n minus n1 minus n2 into and so on. Now, this is cancelled with this one. This is cancelled with this one. So, this will be equal to factorial n divided by factorial n1 factorial n2 factorial n3 factorial ni, and this will be equal to pi I factorial ni. So, the number of ways in which particles in different states may be exchanged, leaving the total number in each state fixed, is given by this one. For Boltzmann system, therefore, for group or level GI, elementary wave functions are available. Among the Ni particles in the ith cell, the first can occupy these levels in GI waves. The second one can occupy these levels in GI waves, because there is no restriction on the particle. It means any number of particles can be accommodated in any cell. Therefore, total number of ways to obtain occupation number Ni or eigenstate for the whole system is given by W equal to factorial n divided by factorial n1 factorial n2 factorial ni, g1 raised to n1, g2 raised to n2, gi raised to ni, or this will be equal to factorial n pi I gi raised to ni divided by factorial ni. Now, W is this one. The correct value of gamma is approximately Wi bar. And what is Ni bar? Ni bar is actually set of occupation number that maximizes Wi bar. So, correct value of gamma E will be this one. And here Ni bar is actually set of occupation number that maximizes Wi bar. Therefore, entropy S equal to K log W Ni bar, not S equal to K log Wn. By using different statistics, Ni bar equal to Gi divided by Z raised to minus 1 e raised to beta ei minus plus 1 if the system is either Bose system or Fermi system, and if the system have Boltzmann's gas, then Ni bar is given by Gi Z e raised to power minus beta ei. Here this negative is for Bose and positive is for Fermi. It means for Bose gas, Ni bar equal to Gi divided by Z raised to minus 1 e raised to beta ei minus 1, and for Fermi gas, Ni bar equal to Gi upon Z raised to minus 1 e raised to beta ei plus 1. Now, Np bar is actually Ni bar upon Gi. So, for Bose and Fermi gas, Np bar equal to 1 upon Z raised to minus 1 e raised to beta Ep minus plus 1, and for Boltzmann's gas, Np bar equal to Z raised to minus beta Ep. because if we divide it by gi, then gi will be cancelled and this I is replaced with p. So np bar equal to z e raised to minus beta ep, and here this gi will be cancelled out and this ei will be ep. So np bar will be this one. Here z and beta are Lagrange's multipliers which are determined using condition E equal to sigma p ep np bar and n equal to sigma p np bar. So by using these two conditions we determine the value of z and beta. Beta equal to 1 upon kt, k is Boltzmann's constant and z is fugacity. And ni bar for Bose and Fermi gas is this one, and for Boltzmann's gas is this one, and S equal to k log Wni bar. Now by using Stirling approximation, S upon k equal to log Wni bar will be this one for Bose gas, and for Fermi gas S upon k will be this one, and for Boltzmann's gas S upon k is given by this relation. Here we use Stirling approximation. Here also we neglect 1 in comparison to ni and gi. So this minus plus 1 is not there. More general formula for S upon k for Bose gas is this one. Here we are not neglecting 1, and for Fermi gas S upon k is this one, and for Boltzmann's gas S upon k is given by this relation. Here we assume that ni square bar minus a square of ni bar is very much less than a square of ni bar. After determining the value of z in terms of n, all other thermodynamic functions can be determined by using above equation. Which equation? This equation. Here we end our session. In today's session, we have discussed about ideal gas in microcanonical ensemble. Goodbye.